So let's say you've got one of these, a satellite, more specifically a 3U CubeSat. They're called that because there's 3 square units in them. And with the satellite, you're looking for the center of mass. Now, you might have learned this in physics class or whatever, and you're like, oh, that'll be easy to find, right? I'll just, apply the formulas that I learned. It's easy, right? But then the issue with a satellite or any complicated object is all this stuff it's not a uniform body. Everything has a different center of mass, and you might have a good 3D model of it, but how accurate is it really? And what if you need to know pretty precisely what the center of mass of the actual full satellite is that you have built? So I set out to build a device that could tell me the center of mass of a satellite like this, and it was harder than I expected. So first of all, I went on Stack Exchange, as you do, and oh, look at this. Someone asked about the experimental method to determine the center of mass for a 3D object. It's non-uniform density and whatever, it doesn't really matter the size, but it's small. Okay, perfect. Let's see what the correct answer was. Put it in a box with packing peanuts and measure it. Okay, this isn't quite gonna work. We need something a bit more accurate than this. Bouncing it on a wooden stick and putting it in a box, right? I asked around at the Rocket Club at my school, and they said they just hold it with their hands, and wherever it bounces is the center of mass. I wasn't getting good answers, so I needed to look further. I found this research article in the International Journal of Aerospace Engineering by Dario Modinini and these lovely people from Bologna, and I was like, oh, great. Small satellite platforms, accurate center of gravity. This is just what I need. And it's simple, too. But what's this? I don't want to be hanging the satellite. It's really expensive, and if I drop it, I'm going to get in a lot of trouble, right? My device can't be dangerous for the satellite, and I don't want to have to install something like this to hang it from, and then use this laser system with the inclinometer and all of this, right? I want something that's simple and accurate and fairly easy to build. So I looked further. I found this report from NASA and I think the Air Force from the late 60s, and they're talking about weight, volume, and center of mass of segments of the human body. Now, it might seem strange, but if you think about it, it's also non-uniform. It's about the right size we're looking for. So, and it's from the 60s, so it's probably a simpler method that's more accessible for us. This might give us a clue about what we can do. Now, this paper is pretty wild. They go through a lot of different past research and how scientists going back to the 1800s found center of mass or tried to find center of mass of human body in full and in parts, and there are all these interesting diagrams like this and over here, kind of freaky. Here's an explanation of the design I came up with and the reasoning behind it. First, I'm going to do a quick review on what the center of mass is. Essentially, it's the point on any body where the mass is concentrated. For a flat shape, like these I have here, it's the point where if you bounce it on a stick, like this, if you bounce like this shape on a stick like this, it won't tip over. It isn't always the geometric center of a body, and you can see that here. This side is heavier and this side is lighter, and so the center of mass, shown in red here, will be shifted over to the heavier side. So if that makes sense, let's get to the design. Here's a pretty general version. This orangey body here is our example object that we want to find the center of mass for. Let's say that it doesn't have a uniform density, just like the bar from the last page or the real satellite that we're trying to measure, right? We know that the center of mass is somewhere, and the force of gravity is acting at that center of mass. So if we want to find where the force of gravity is acting, we can find where the center of mass is. So if we find where the force of gravity is acting, we can find where the center of mass is. They're the same. For this to work, we need to focus on the reaction forces, these forces that I've shaded in blue that are stopping the force of gravity from pushing the object down. If we make it so that there's only 4 very small contact points that are pushing up against gravity pushing down, it's not difficult to find information about these forces that would let us find the location of the force of gravity. So here's a top-down view of these forces. You can see that I defined a distance A and a distance B, which make up the horizontal and vertical distances from the center of mass, which is the same as the force of gravity in this case, as I already mentioned. So here I've written the equations for these A and B, where F1, F2, F3, etc. are the magnitude or amount of force, which can be measured just by using like a simple scale, right? Here's a quick explanation for why these equations work. So this explanation requires the concept of moment, which is also called torque when it's about force. Moment is defined as force times distance, and moments represent a rotational force, you could say. Since this whole setup will be stationary, it's not moving, it's not rotating at all, we can say that all the moments, which are the forces that would cause, in this case, a rotation around the x-axis, which we defined up here as being along this line, equal to 0. So nothing is rotating this way. And so we say that all the moments are 0. If all the moments equal 0, it doesn't move, which is the correct state for it to be in. Now we can write this equation, which is just all of the forces times distances equals 0, which we said earlier. And you might think there's an issue here, because we know F3 and F4, and obviously we know 100 millimeters, but we don't know FG and we don't know B, so if we try and solve for B, it'll be in terms of FG and everything else, so it doesn't work. However, if you look here, the force of gravity of the object has to be the same as all of the forces pushing up combined. So we just set the force of gravity equal to all those forces. And that's how we get this equation. It's pretty simple, but seeing it in the real life can also build a better intuition of it. So let's do that now. And you can see here, all the pieces are getting printed out. All right, it's done. So let's take off the printer. Now that we got everything printed, we can do a little test fit to make sure that this is looking good. Fits pretty well here. The satellite will sit in here along the rails, just like you talked about in the CAD. So just doing a bit of a stress test to make sure that this joint holds up, because I didn't really think about it a lot earlier, but it might not be strong enough. But we'll see. The satellite's about 4 kilograms, so this should be enough to test. Okay, it's definitely bending a bit, so I might need to add some kind of support here to stop that from happening. But because it'll change the distance between these supports. One important step of this design is I need to check whether my device actually works, right? So the way I'm going to do that is I'll take an object where I know the center of mass of it, it's easy to find, and then put it in the device and see how accurately it works, right? Let's take this monster, for example, as a test. If we measure it here, you can see it's about 16 centimeters long, so 160 millimeters. Now, let's take it over and put it in the device. Zero it out, so we're reading 0 grams there. Put this up against this back wall here, and now reading 116 grams. So Let's also measure total weight there. So 496. Let's just write that down. 116, 496. So measuring the distance from here to here, it's about 340 millimeters. So now that we have these numbers, 116 grams and 496 grams, we could convert them into forces, like divide by or multiply by 9.81, but it's really not necessary since they'll be divided by each other and the units will just cancel out either way. So the total distance between the supporting forces here that we found was 340 millimeters. And let's just plug that all into our equation. So instead of this 100 millimeters, we'll have 340 millimeters because that's the dimensions of the real device that we've come up with. So this F3 over F4 is really just one measurement that we took here. And then all this bottom part is, like I said, FG. So that's just the mass of the can. So we'll have the center of mass of the can equals 116 over 496 times 340, and that, take the calculator here, times 340 equals 79.5. And if you remember from earlier, we measured the can to be about, this is millimeters. We measured the can to be about 160 millimeters. So obviously, if you multiply that answer by 2, you'll get 159.03 millimeters. And these are this is really close. So I would say this is a really good showing. If you want to talk about in terms of percent error here, 159.03 minus 160 over 160. I mean, this is like a 0.6% error. Obviously this measurement wasn't very accurate, so for something better you'd want to get better, but you can see that this really works and you don't need a crazy setup to find stuff like this to a really precise enough degree. So yeah, that's pretty much it. Thanks for watching, and hope to talk again soon about something interesting in the future.